leave that in. Hey everyone, it's me, Ray Long. This is another episode of Full Stack Distributed Systems. We've been working on our topology and weight evolving artificial neural network inside of our universal wargame engine. So we're almost done with our machine learning component. Basically, we're going to finish off all the mutations, finish wiring up the neural network, and then we're going to go ahead and jump back into Unity as soon as we can and bolt the neural network into our game engine. And then after that, we'll continue working on our game engine, and we'll also start working on some infrastructure automation and start building headless versions of the game server and getting them up into the cloud. So we've got a lot to do over the next few episodes, and thanks for following along. As always, thanks for liking and subscribing. Check me out on Patreon. All the links down below. I don't want to bore you, so we just head on over to Visual Studio here. Oh, there we go. We'll get some music. Alright, so where we left off last time, we just finished our connect to random neuron mutation, and we're going to go ahead and start working on the next mutation, right? So we have our base mutation class and our I mutation interface, and we have our first mutation called connect neuron. So what's next? Very good question. This is going to look pretty similar, but slightly different. Similar idea though. Instead of connecting two random neurons, we're going to connect two random synapses. So why don't we just copy and paste this, connect neuron class. There we go. Uh-oh, things are going a little slow today. We'll call it connect synapse. Let me just free up some RAM here real quick. Oof. All right, go. I'm gonna call this connect synapse. So we need a neuron from, neuron to. And then we need an inserted synapse. Okay. We need to do anything, we don't need any kind of crazy constructor. That's good. And we don't need an activation func, so that's good too. Alright, so what are we going to do in mutation? Well, we can get rid of all this. We don't need it for our synapse connector. Okay. And let's just get rid of this too. Alright, so mutation. First thing we're going to do is we're going to recite the metrics. Are we going to re-choose it? For now, we'll say false. Now we're going to have another do loop here. But this time we're going to say while, not whole. Sheesh. So while re-choose equals true, we're going to do this. First thing, make sure when we re-enter the do loop, Say re-choose equals false again. Okay. I say neuron from is going to equal, we need the neural network helper, or the neural network utility. We're going to get a random, oh, excuse me, that's not correct. Network dot get random neuron. Fantastic. And neuron 2 also be random neuron. You know what? Let's change the I want to change the implementation of this. Let me just see what this looks like real quick. Alright, this is what we want. We want min value max. This is much cleaner. So there we go. Well, now we're less ridiculous, but we still want to do the Mersenne twister. Alright, that was bugging me last night. I went to bed thinking about it. I was like, it's just not good. There was some bad, ugly, hacky code that tried to... Anyway. We're going to have our loop condition here. If neuron from dot distance is less than or equal to neuron 2 dot distance, we want to re-choose. And we'll go ahead and continue. That means we want to break out of the loop, right? Okay, now, if neuron 2 dot input synapses exists, that's a list. What are we going to say here? Well, let's pass in an n. We'll say n dot no. The input is equal to the neuron from all right, let's break that down. So we can just say that exists. So if neuron 2 dot input synapses that exists, all right, so basically it's saying if the neuron that we're sending to, okay, and its input synapses, if we already have neuron from, we need to re-choose, because otherwise no mutation is going to re-choose if input re-choose, otherwise we won't mutate. right. Okay, so now after we've chosen our stuff, now we're going to do. It's going to look pretty similar to what we did before. We're going to have a new synapse. And we're going to again get a random weight. So actually I probably didn't need to delete all that stuff. But what are you going to do? Okay. We have our inserted synapse. What? Oh yeah, okay, so. Oh, damn it. I always do that. Alright. We're going to add the inserted synapse. Very good. Then, of course, and now we need to add our inserted synapse to the actual network. Otherwise, we'll get bizarre errors that are going to be hard to track down later. And now that we've done this, we need the network to recite its metrics again. Did I implement that correctly? Let me just double check. Oh. There we go. Alright, cool. Alright. Now, here's what you want to do. Now, if we have a loop, if loop is detected, okay, we need to roll it back. Network, we need to take each of these neurons. And we want to call reset on each of these. And now we have to go into our rollback logic, which is, see, that's the reason why we store these things that we created in our field, so that if we need to roll back, we've got them stashed in memory somewhere. So anyway, so neuron 2, we need to input synapses dot remove, well, the inserted synapse. I still don't like the name of that. Control R, Control R. Alright, cool. I think I just broke my code. Yep. Alright. That's it. That's how we connect synapses randomly. Easy, too easy. What's next? What's another useful mutation we might have here? Well, we have our multi-mutator. It's always a classic. Always a classic. Call this multi-mutate. It's going to be even easier than the ones we've already made. This is real easy. Okay. Oh. Well, that was the wrong thing to... yeah. Oh, it's still early over here, guys. Let's do our multi-mutate. You're like, why are you copying and pasting? Because I don't like the name. I don't like messing with my namespace. It doesn't matter. Wait a minute. Okay, good. Okay, multi-mutate. Let's get to work here. So, let's get rid of this. Okay, so multi-mutate couldn't get any easier. All we're going to do is we're going to have a public list of mutations. We'll call it get private set. Fantastic. Now we need a constructor, only one constructor. Multi-mutate. I accept a list of mutation objects. Ugh. See, so mutations. Oh no. Oh. All right, there we go. Now this, as you imagine, is going to be super easy. Our M in mutations. What do you think we're going to do? Obviously, we're going to call mutate. Ugh. What? Oh yeah. Pass in the network. That's it. That's how you apply all the mutations. Rollback. Gonna be pretty easy. But we have to do it in reverse order, so let's see, goes mutations.count -1 because we don't want off by 1 errors. Oi. Equal to 0. So basically, for this for loop, we're actually going to be okay. So here we go. What's going on here? So when we do the mutation, we call mutation here in multi-mutate. We're taking our collection of mutations and we're iterating over them for each in a forward rolling cycle, right? And so you can say maybe the wheel rolls forward a whole rotation, right? But in order to undo that, you just don't roll forward and you don't just keep rolling forward and then unmutating. You're going to get a whole different network than the one that you started with. So what you need to do is unwind the cycles of mutations that have been applied. So now we can say mutations rollback mutation. Now this is very powerful. This means that we can assign collections of mutations to a multi-mutate and just throw that into our neural network. And you know, certain collections of mutations can be classed together as their own. Well, I'll give you a hint. Enough mutations together in a coherent form create a new species. So, you know, creating useful collections of mutations is the foundation by which we're going to start differentiating interesting new species, quote unquote, in our neural network. So, all right, so multi-mutate's done. What do we got next? We're just cruising right through here. Multi-mutate. Oh, here's a good one. We're going to do a random synapse reconnect. So okay. Now how are we going to do this? Well, we don't need the constructor. Don't need that. Get rid of that. You know, it'd be interesting having our neural network randomly change stat lines in our Wargame engine bounded within a bounded range. You know, basically, we can have the rules enshrined, like, you know, roll 1d6 on a 4 up, you get +1 to your speed or something like that. You know what I mean? Those rules can be enshrined in a mutation. So we could do all sorts of interesting stuff. Doesn't matter. Anyways, we want to teach our neural network how to load it up with different detachments and have those detachments fight. And we want the neural network to learn how to build detachments and all sorts of fun shit that we're going to try to train it to do. Whew. But we got to build the neural network first. And if you remember, we already have enough of a working game engine to actually build something meaningful with it. So anyway. Alright, so we need a private variable called synapse. And we need something that implements iComputing node. This needs to be the old destination. And how do I mutate? Okay, so turns out that synapse is going to get random synapse. We haven't implemented that yet. go ahead and implement it. Let's see. Let's take this. Let's put it next to our random neuron, right? Come on. There we go. I remember I made specific properties. Okay. Well, that just means, you know, if we want to do, we already have the properties, so we might as well use them. So, all right. Pretty easy. So we have a random synapse. That's good. Our old destination is our synapse dot input. Oh gods. Okay. Now we're going to say synapse dot input equals, I think we're going to, this is actually going to get a random node. Okay, and then let's go to this. We can't navigate to the symbol because it doesn't exist. Okay, let's generate that symbol. Symbol. So how are we going to get a random node? So we need to implement iReceptor, right? So all we're going to do is dot what are the may as well be consistent. Turn there we go. Now we have a random node. Okay, this couldn't be any easier. All we're going to do is say synapse dot equals old destination. Oh, look at that. We have a uh-oh. There we go. Because iReceptor actually implements iComputing node. So there we go. Easy. Too easy. Okay, what's next? Well, we can remove a neuron. That, of course, changes the topology. So uh, hmm. We can also remove a synapse. I don't know. I'm not sure how I want to do remove neuron. So let's do remove synapse. Okay. Remove synapse. You know what I want to do? I'm going to copy this and rename this. Empty mutation. Call it placebo effect. That's funny. There's actually not a real placebo effect because placebo effect is a measurable effect and we're not measuring anything. Well, we can always measure how many placebos we have, so there you go. Anyway, remove synapse. What do we want to do? What the fuck is this song? I'm going to remove. Quick song change. Alright, we need our remove synapse. We need a record of that. We need our. Here we go. So we need to have some way to check our failure mechanism. Give me that random synapse. Now, if we need a little bit of logic here. Dot synapses. Wait, what is this? Okay. If it's actually less than 3, we'll get into the numbers later. Or network.effectors.exists. Oh, that's a S. All right. Made you some parentheses just for fun. Oh, duh. Don't need extra parentheses. Okay, that's a little easier to read. So here's the thing. If our synapses are less, if we have fewer than 3 synapses, we have a problem with our neural network. We're not going to be able to make enough connections. So that's a big issue. All right. Yeah. Let's get the first neuron. Oh, wait a minute. What am I doing? Ugh. My hands are going faster than my brain, which is not good. Okay, so here's what we're saying. Network, neurons, first. Okay, so our from neuron, we're going to have the network, and it's neurons, and the first one with the input synapses that contain the removed synapse. So, we're basically just going through and getting the first one. Link makes this so easy. So now we take those input synapses and we remove. Easy. Now, so our network doesn't try to do anything funky with it again. If we fail, just return. Of course, then we'll just go ahead. Alright, so we're actually going to do the same thing here for neurons. Because, fuck it, why not? Rename. We're going to call this remove neuron. know what? I don't want to do remove neuron yet. I don't feel good about it. I have to do a little more. I have to go check my notes later. Alright, so we're removing the synapse. Alright. Well, we could mutate some weights. That's actually a really good idea. Just take our placebo effect. Oh, you know what we could do for our placebo effect? There we go. What does clone do? Hmm. You know what we could do? We'll just leave it like that. Yeah. Okay, so our placebo, we're going to have a weight mutation. We're going to call this a weight changer. Okay, so we need, because we're talking about synaptic weights here, so we need the modified synapse. Alright, we need the old weight. What do we need? We need a dictionary of synapses and doubles. We're going to call this success mutations. Call this successful. That's too bulky. Call them failed mutations. Here we go. You know what? I always do a new. There we go. We don't have to. We don't want null pointer exceptions later. That's a pain in the dick. Alright. So can improve next is going to equal true. Modified synapse equals. Look at that random synapse. Live by the RNG. Die by the RNG. basic bookkeeping here. I'm going to say modify synapse. That way, you got it. I'm going to get that random weight. All right. Very good. Well, okay, so successful. If you can't improve next, throw unable to improve. Okay. Now let's implement our improve method. Okay, I'm just running. My battery's rapidly running out of time. I got 16 minutes left. All right. So let's go through this quickly. I'll call it step back, old weight equals old weight. Old weight equals weight new weights equals the old weight plus weight minus step back old weight We're just going to skew it a little bit here. So now, if math.round new weight minus old weight okay, that equals 0. Can improve next equals false. If the new weight is greater than 2, So we want to make these bounded, right? Else if new weight this. These are our bounded ranges for our weights. Modified synapse dot weight equals new weight. Okay. Public bool. Oh, my bad. I know my batteries are on. Thank you. Let me knock down my brightness a bit. Squeeze out a few more minutes here. We got 11 minutes. Okay. All right, so we need to do a little bit of math here. Equals can improve next. And absolute. Oh, right. And that's it. Okay, I got, let me just see real quick here. Oh, we have one more big mutation, which is connect neuron between. So, anyway. All right, everyone. Thank you so much for tuning in. We covered a lot of ground today, working on our mutations, and I'm really happy with the progress that we've made today. Our neural network is almost finished. I believe we're going to be able to finish it up in the next 1 or 2 episodes, and that'll be the time that we start plugging it in back into the game engine. So thank you so much for your patience and your support. It means a lot to me. I love all of you guys so much. Thank you so much for all of your patronage and all of your support and all of your fandom and everything else.